If you're in AP Chemistry, that must mean that you absolutely loved chemical reactions last year. This video looks at the different kinds of reactions, and hopefully it's kind of a review of what you did second semester in a first-year chem course. So a lot of this should be relatively familiar to us. We're going to start out by looking at synthesis reactions. In a synthesis reaction, the key is that there's only one product. We can join 2 reactants, we can join 10 reactants, but we only form one product. So some common synthesis or composition reactions might look like this. And most of these are probably things that you could have done last year. If we had a metal plus oxygen, we form the metal oxide. If we have a nonmetal and oxygen, we form a nonmetal oxide. Now, the one big difference between these two is that if I have a metallic product, it's ionic. Well, we might mark a little note in there. Ionic compounds always have a metal, nonmetal. So if I have magnesium reacting with oxygen, I'm going to form magnesium oxide. I can write the product just by looking up the charges on a periodic table. I cannot do that with the nonmetals. The nonmetals don't transfer electrons. They're sharing and forming covalent compounds. So I don't know if this product's going to be carbon monoxide, carbon dioxide. So they'll have to give you a little hint on that one. So a question might read like, solid carbon reacts with oxygen gas to form carbon dioxide. And then I write the balanced equation. The other thing that we should make note of, a rookie mistake, with those ionic compounds, sometimes people read these as Mg plus O2. Well, by golly, that must form MgO2. And then we'd say, no, you're crazy. That's not a compound. That's not neutral. So just because the oxygen is O2 diatomic on its own does not mean that the oxygen is O2 when I bond it with some kind of a metal. Then in the new product, I look up the charges if it's metal, nonmetal. If it's covalent with 2 nonmetals, I'll be given a hint as to what that final product might be. Kind of the same gig with the last two. Sodium plus chlorine forms sodium chloride. It's not NaCl2. We would balance this with its charges because this is another ionic compound. It's got a metal in there. The one below it, I would have to be given a little help. If I've got phosphorus reacting with chlorine, I can predict it's going to form some kind of phosphorus chloride compound. It will be covalent because it's all nonmetals, but I don't necessarily know the formula. I can't just look on the periodic table and always predict that since it's not ionic. I'm not going to use charges. It could be a phosphorus trichloride. There's a phosphorus pentachloride. So in that case, they'll tell you what the exact product should be. Another thing that we should make note of are these diatomic elements. Diatomic elements. And they kind of form a pattern on the periodic table. We've got hydrogen, and then over in the nonmetal area, we'll have nitrogen, oxygen, and all the halogens, fluorine, chlorine, bromine, iodine, and astatine. When these guys are in their elemental form, the formula needs to be diatomic. So like magnesium plus oxygen gas. The elemental oxygen gas is O2 diatomic. Or the chlorine gas is an element diatomic. But most elements are not diatomic. Most elements on the periodic table are metals. And then it's just the regular symbol. Sometimes people kind of get that confused. So it really is just sodium, Na. Phosphorus is not diatomic. It's a nonmetal, but it's not one of the diatomics. So I do need to kind of remember which elements are diatomic only in their elemental form, meaning they're not bonded to anything. Now, these would be equations that you could have done in a first-year chem course. Then we usually just look at binary compounds in synthesis and decomposition reactions where there's only two elements. So here you're just going to slap them together and form a product. In AP, there are a couple kind of special reactions that we should be familiar with. And so these might be ones that would qualify. If you have a metal oxide in water, you'll form a base, a metal hydroxide. And again, you can always find the formula by looking up the charges. If I know that it's going to be magnesium hydroxide, just look up the charge of magnesium and hydroxide to get the formula of the product. Non-metal oxides in water form acidic solutions, and they're usually pretty predictable. You're going to have a real common polyatomic. So like carbon dioxide in water will form carbonic acid or hydrogen carbonate. You could have a sulfur oxide in water, and you'll form sulfuric acid hydrogen sulfate. A phosphorus oxide in water would form phosphoric acid hydrogen phosphate. So these would be some common reactions that, on paper they look pretty boring, which is why we'll do a lot of these reactions in the lab or as demos so that throughout the year you kind of see, okay, well, what I put on paper really does work. Oh, yeah, if I do put carbon dioxide as either a gas or maybe a solid like dry ice, if I put that in water, the final product is acidic. We can test for stuff like that and prove that these reactions on paper really are happening in the lab. So I get it. Like watching these reactions on video or looking at them on paper kind of sucks. But we're going to do a lot of these in lab and as demos in class so we can prove that it's right. I promise it is. If you can handle the synthesis, the decomposition is just the opposite, where I have one reactant breaking apart into multiple products. And again, some of these would be easy things that you could have done in a first-year course. The binary compounds like water, sodium chloride, mercury oxide. If there's only two elements in the compound, all you're going to do is break them apart into the individual elements. Water breaks down into hydrogen and oxygen. Individually, both are diatomic. Sodium chloride breaks down into sodium and chlorine. Only the chlorine is diatomic as an element. Mercury oxide is an orange solid. We used to do this when you'd heat it in a test tube. And it really would form oxygen and little beads of liquid mercury, which were kind of fun until you had to figure out what to do with the mercury. We should note, too, that these decompositions are endothermic. There we go. Endothermic. You have to add electricity or something's heated. Compounds are stable. Most elements want to be in compounds, so they have full outer shells. So if you're going to break apart a happy marriage, then you've got to have some kind of an energy source. Electricity, heat, those are probably the most common. Now, again, there are some common decompositions that have more than one element involved, or they maybe break down and form some smaller compounds instead of just the individual elements. Two of them that would be kind of simple would be this guy and this guy, because we just kind of mentioned them. It's the opposite of the synthesis. If you heat a metal hydroxide, you'll form the metal oxide and water. And again, I can just write the charges to find the product of the metal oxide. The non-metal oxides are formed when you heat the acidic solution. So like if you heat sulfuric acid, you'll form water and a non-metal oxide. Or if you heat carbonic acid, you'll form water and carbon dioxide. These are a little harder to predict the formulas. Like, how do I know? Is this SO3? Is it SO2? There are a lot of different versions of sulfur and oxygen. They'll tell you. You'll be given hints for those covalent compounds. So they might say something like, sulfuric acid is gently heated to form water and sulfur trioxide gas. And then all I have to do is write the equation and make sure that it's balanced. Other ones that will run in the lab, carbonates. Love to break down and form carbon dioxide gas. This is very, very, very common. It could be a metallic carbonate, like calcium carbonate, or it could even be something like a bicarbonate, like sodium bicarbonate. When you bake with sodium bicarbonate baking soda, it decomposes, and one of those products is carbon dioxide gas, and that's what makes your cakes rise and all that good stuff. So these are real common. And again, you can find the formula of the metal oxide by using its charges, because it's going to be ionic. Another one that we're going to run in the lab. Actually, we might run this one a couple times because it's so cool. Chlorates have a tendency to decompose and form the chloride and oxygen gas. Now, the bottle will always have all these warnings on it because oxygen gas is required for combustions. Things burn in the presence of oxygen, which is exactly what we're going to do with it. We're going to take these chlorates. We'll use some potassium chlorate. We'll heat them gently, and you don't see the oxygen, but you can prove it's there by putting something in its presence that will burn. The other product is just the metal chloride. So you could have like calcium chlorate. It would break down and form calcium chloride and oxygen gas. And then I just balance them appropriately. And this last one too. We'll do this one throughout the year multiple times. I love this reaction. Hydrogen peroxide is the close cousin of water. Real similar, but it's H2O2, and that extra oxygen changes its properties. If you ever gargle like hydrogen peroxide, you'll notice that it's kind of fizzy. It breaks down to form water and oxygen gas. So water is much more stable than hydrogen peroxide. Another just common decomposition, one that the more you do it in the lab or the more that you see this reaction and we prove that it's water and oxygen, you'll kind of get used to it. For a while, you may end up looking up some of these kind of goofy decompositions, but they are all ones that will run at some point. So hopefully that'll kind of get you more comfortable with some of these decompositions that may form smaller compounds instead of just individual elements. We've mentioned the combustion. The combustion is when I have an organic carbon compound burning in oxygen. The reactants are always an organic compound and oxygen. And these are always exothermic. Something's burning in the oxygen. We're going to do something similar with that decomposition of the potassium chlorate. We'll do that first to produce a bunch of oxygen gas, and then we'll use that oxygen in a combustion. You're going to love it. It's one of my favorite reactions of the entire year. The only thing that changes here is the identity of that carbon compound, that organic compound. Otherwise, 75% of a combustion equation is always the same. These are a little different, but the rest is all the same. It's a carbon compound burning in oxygen to form carbon dioxide and water. Always carbon dioxide and water. You don't have to do a replacement. You don't have to look up charges. These combustions should be a piece of cake. They should be kind of no-brainers. Now, they used on the product side those arrows. Often I just use gas. Carbon dioxide is a gas. And because these reactions are exothermic, the water is often a gas. CH4 is methane or Bunsen burner gas. When you light the Bunsen burner, you don't see water droplets raining from the sky. Now, it's exothermic. The water evaporates. So it's formed as water vapor. Now, we'll do several different combustions throughout the year, too. And some of them don't burn as hot. They don't release as much energy. So we may be able to get some liquid water and at least prove that water is one of the products. So don't let a combustion get the best of you. Sometimes people kind of forget about it. But it's really supposed to be kind of an easy reaction. The identity of the carbon compound will change, so I'll have to balance it differently. But it's always a carbon compound burning or reacting with oxygen to form carbon dioxide and water. And the last two reaction types that you probably looked at last year were the replacements. You may have called them single replacement or single displacement. The key here is that we have one single element reacting with a compound. And there were a couple rules when it came to predicting products of these replacement reactions. The first rule was like charges can switch. So for example, in this first one, it kind of looks like the iron must have been +2. Copper's +2. Sulfate's always -2. If the single element, in this case iron, is positive, he can only switch with the other positive. Like can switch with like in terms of charge. And now once you switch those charges, make sure you check the charges on any new compounds formed. So I just formed a new compound. Now it's iron sulfate. Always check those charges to make sure that you have a neutral product. The other thing that I would check is that new element. Is it diatomic? Copper is not. So I just leave it as Cu copper. And then I may or may not need to balance the reaction. This zinc and acid, this is real common. We'll run this one. Zinc in this case is +2. We're going to put it in some hydrochloric acid. The zinc is positive. He can switch with the other positive. Now, it's okay that it's a +2 switching with a +1. That's fine. As long as it's positive for positive. Because if I'm going to bond somebody new with chlorine, chlorine's always negative. He can only bond with something positive anyway. And when I make that new product, I have to check the charges. Just because there was one chlorine on the reactant side doesn't necessarily mean they'll start with one chlorine on the product side. Depends on what I've bonded it with. Now my other product will be hydrogen, who is diatomic when he's as an element. So that would be something to look out for. And then finally, once I'm pretty confident I got the products written, I would balance the reaction. Now something like this guy, chlorine is -1. Sodium's +1, bromine's -1. This one stumps people a lot. If the single element is negative, he's really only looking to switch with the other negative. So don't get into a habit of saying, like, just switch with whatever element is first in the compound or something kooky like that. Now, you got to kind of think about the charges. If you're going to bond something new with sodium, it's got to be another negative. And then I would write my formula, check my charges, and then I would just check to see if that other element is diatomic, which bromine is. Another one that is commonly missed, and I feel like we can run this thing 10,000 times in the lab, and on paper, people still get it wrong. It drives me insane. So this might be another one to put a star by. It's kind of a special reaction. It's not exactly what you'd expect. Metals. Some of the metals will react well with water. Obviously, some metals don't react with water at all. But your group 1, group 2 metals, they'll react with water. Sodium in water is a pretty common reaction. It's kind of a fun one that we'll run. Here's what people will do wrong. Okay, so I'll put a sad face down right away. This is the wrong answer, but it's real common. They think they're doing everything right. Sodium plus water. La-di-da. Sodium is a +1. Hydrogen's +1. Oxygen's -2. So they think, let's do a little switch with the sodium and the hydrogen, right? So on the product side, they'll say, okay, we're going to kick out the hydrogen. So now hydrogen's all by himself. And by himself, he is diatomic. And then we're going to bring sodium over with oxygen. Sodium with oxygen. And we'll check our charges. Gosh, I'm such a perfect little chem kid. I need 2 of those and I'm done. My products are hydrogen and sodium oxide. And then they get it marked wrong and it's tears. It's like instant tears. It's tragic. How could I have that wrong? I thought I followed all the rules. This is kind of a goofy one. When you put a metal in water, that metal actually will only replace one of the hydrogens. Right now, it's kind of like I've kicked out 2 hydrogens and then I'm putting the sodium with the oxygen. The sodium will actually only replace 1 hydrogen, leaving behind hydroxide. Oh, so here's what I do. When I have water on the reactant side, instead of writing it as H2O, I'll write it a little bit differently. I'm going to have a little more room. This may help. Think of water as hydrogen hydroxide. Oh. So now if you have +1 sodium, +1 hydrogen, -1 oxygen, and you make the switch, we were half right. We're still going to get hydrogen diatomic, but then our other product is sodium hydroxide +1 -1. And I get it. On paper, people are real frustrated. Why isn't the first one right? I mean, I followed all the rules. I made sure everything balanced, and I could balance the equation if I needed to. It's just not what happens in the lab. In the lab, when we really run this thing, your product is a base. We'll use phenolphthalein and all kinds of different indicators to prove that the product formed is a base. So then we know that it must be that second version because hydroxides are basic solutions. So that first one gets a sad face, although that's a very common wrong answer. But whenever you have a metal that reacts with water, you will always form the metal hydroxide. And then hydrogen gas is the other product. The one product will always be a base. So make note of that one. That one comes up throughout the year, and it's a real common reaction. So it's one that they like to throw on the AP test, too, to kind of trick you. But we're going to run it enough that hopefully we'll remember that the product of a metal and water is always a base. And then finally, the double replacements. The double replacements often form precipitates or maybe sometimes gases. Here's where you're going to have 2 compounds on the reactant side, and there's a double replacement. You don't have to worry too much about charges. Just again, know that positive can switch with positive, negative can switch with negative. Or sometimes I'll kind of just say, I'll switch the first 2 elements, or the first element in each compound, +1, -1. If I'm going to form new products, it has to be a positive-negative ion combination. So if I switch like silver and sodium, then I should get appropriate products. Sodium with nitrate, silver with chloride. And again, I always have to double check those charges. Not this one, they're all +1, -1, so it's fine as is. But let's say I have barium chloride and sodium sulfate. When I switch those ions to form sodium chloride and barium sulfate, I need to double check my charges. Same thing with this hydrochloric acid. +1, -1. This must be a +2 because sulfur is always -2. You can either switch the positives or switch the negatives. It doesn't matter what order you write your products. But now if I put iron with chlorine, I need to fix this formula. There needs to be 2 chlorine. Or if I have sulfur with hydrogen, I need to fix that product. And then we'll balance it appropriately, which they must not have done. So let's throw a 2 in there. Yeah, that's a messy looking 2. But it makes me feel a lot better. It's balanced now. You might form water. This is real common in a neutralization. An acid usually has hydrogen and a base usually has hydroxide. So if you were to do this switch, one of your products is hydrogen hydroxide, often written as water. I don't care which way you write it. If you write HOH, everybody's going to know you mean water, hydrogen hydroxide. That is totally acceptable. And then finally, there are a few products that further decompose. So this might be kind of a special one. If I look at this guy, calcium carbonate, hydrogen chloride. At first, I want to do this switch with the positives. I'll switch the like charges. So I would get a hydrogen with carbonate. And I get calcium with chlorine. And then I balance these guys. +1 minus 2. I need 2 of those. +2 minus 1. I need 2 chlorines. And so a lot of people will leave the products here. They'll leave the products. I did the switch. I checked my charges. And they'll balance it with a... Oh, this will make me feel better. With a 2 in front of the HCl, right? That's a messy 2. However, carbonates love to decompose further. So we've got that calcium chloride solution. That's all good. But this guy has a tendency to further decompose and form carbon dioxide and water. We're going to run this exact reaction in the lab. And it's kind of funny because everybody will write down when they put their observations. They'll say, oh, it's fizzing and it's bubbling. But then guess what they write as their products? They'll say, oh, the products, hydrogen carbonate and calcium chloride, both solutions, aqueous. Wait a second, you just told me something was fizzing and bubbling. But you have nothing reported on the product side that's a gas. Some products further decompose. Carbonates are always one to look for. They'll further break down into carbon dioxide and water. So here are the ones to kind of keep your eyes out for. When these guys are on the product side, they will further decompose. That carbonate, hydrogen carbonate, will always break down into water and carbon dioxide. This could be H2SO3. Sometimes it's H2SO4 can do this, where it'll break down into water and then like a sulfur dioxide gas. We're not going to do this reaction because it stinks really bad. But that would be one to look out for. This is real common. So actually, these are probably the most common. Ammonium hydroxide has a tendency to break down and form ammonia gas and water. You'll smell it. You'll smell that ammonia gas. Well, yeah, ammonium hydroxide is really a solution of a gas in water. And that ammonia gas doesn't like being dissolved in water. So keep your eye out for these guys on the product side. And when you do your double replacement, if you find that these are one of your products, then we need to further break them down into water and their corresponding gases.